All right. Good afternoon. We'll start. Right. So I hope my audio is loud and clear. Right. Good afternoon. Right. We'll start. Okay. Today, as we are planning, we are starting optics. Right. Optics. 1 second. Right. As we planned, we are starting optics. Right. We are starting optics, and when comes to optics, right, there's a importance of gravity. Is there anything wrong in the YouTube live? No. Okay, now it's fine. Right. So when it comes to the lesson optics, right? When it comes to the lesson optics, in terms of gravity, again, this is a lesson with very high gravity, right? This is a lesson with very high gravity, and this is actually the second part of the unit, oscillations and waves, right? And this is coming under waves. Actually, this is coming under waves, right? This is the second part of oscillations and waves, right? Now, so far we have finished all the waves parts, right? Oscillations and waves means wave phenomena parts, and now today we are starting the second part here, that is optics, right? So when it comes to optics, is the gravity of the lesson, right? When it comes to optics, the gravity is like this, right? From optics, it is contributing for 3 to 4 MCQs, right? It is contributing for 3 to 4 MCQs, right? And there is a structure essay, right? Number 3, actually. Structure essay number 3 coming from optics, right? So one structure essay. And essay number 6 is also the relevant essay for this unit, right? Then one essay is also coming. Then in terms of the marks, 3 to 4 means, let's say 3 marks here, right? If we consider the lower end, 3 marks. And one structure essay is 20 marks from 200, and one essay is 30 marks from 200, right? So when it is taken down to 100, this is 3 marks from 100, and this is 5 marks from 100, this is 7.5 marks from 100, right? Then altogether, that is like 15.5 marks, from 100. So as a lesson, it has this kind of a higher gravity. As a lesson, right? So basically, it is going to be responsible for around 15 marks out of 100, right? It is going to be responsible for 15 marks out of 100. That's a considerable amount. That's a considerable mark, right? When it comes to optics, right? So if anyone needs to take this down quickly, you can take it down before we jump into the lesson. Right. Okay, listen now. So when it comes to the lesson optics, right? To get the approach, I'm going to link this to waves again and going to get the approach from there, right? So we knew electromagnetic spectrum from waves, no? Right? We knew electromagnetic spectrum from waves when we were discussing about electromagnetic waves, right? When we were discussing about electromagnetic waves, you got to know what electromagnetic spectrum is. Then in the electromagnetic spectrum, right, we had, see, in the electromagnetic spectrum, we had cosmic, gamma, X, UV, visible, IR, micro, satellite, TV, and radio, right? And along this direction, lambda increases, right? Lambda increases, and along this direction, frequency increases. Right. Then here we have visible light. Here we have visible light. In visible light, we had 7 different colors. In visible light, we had 7 different colors like this: violet, indigo, blue, green, yellow, orange, red. Right. And this lesson is all about this visible light part in this electromagnetic spectrum. Right. This lesson is all about this visible light part. Right. Basically, the light means visible light. Right. Optics means that is all about visible light. Right. Then we are going to learn about this in depth. Right. You are going to learn about this in depth under this lesson. We are going to discuss about this in depth under this lesson. Right. So this is where optics is coming into our thing, and this is how it is linked to waves, and some of the things we have already done in the wave phenomena, right? With the some of the things, So otherwise, if you are starting from optics, right, you can start from optics as well as a first lesson, right? There are small links with waves that you can get to know with the rhyme, right? So first take this down. Take it down. Take it down. The main thing when you are learning optics is, right, so always focus on the marks, and as a lesson is easily gettable marks if you know these theories from the fundamentals very clearly, right? They are not going to be easy to score, right? They are not going to be difficult to score, right? It's actually an easier part to score, right? And easier part to score. You can score without any hassle when you know about this properly, right? Write down below this. Since visible light slash optics, since visible light slash optics is a type of electromagnetic waves, all features of electromagnetic waves all features of electromagnetic waves are valid for visible light. All features of electromagnetic waves are valid for visible light. All features of electromagnetic waves are valid for visible light. All features of electromagnetic waves are valid for visible light. Right. So one more reminder that I wanted to give you is now, as you all know, we are going to start graded and ranked papers, right? Next week onwards, right? So the class will be starting, the graded rank paper class will be starting on next Wednesday, right? Next Wednesday the class is starting, and for the writing of papers, you can write papers either physical or online from Thursday to Saturday, right? From Thursday to Saturday. If you are writing online, you can do it on the LMS. If you are writing physically, you can write it at Leesa, right? And you have to submit your paper before Saturday, and on Saturday it will be submission will be closed and it will be taken for grading, and your graded papers, graded and ranked papers will be given to you on the discussion day. Discussion will be happening on every Wednesday from 7 to 10 as usual. That was our usual time of the paper class, no? So discussion is happening on the same day as usual, right? Okay, then write down below. Next point, use a red pen. Next point, use a red pen. Write down below. Any wave slash optical ray, any wave slash optical ray, travels through a medium as the product of refractive index, and velocity as the product of refractive index and velocity remains constant, as the product of refractive index and velocity remains constant, as the product of refractive index and velocity remains constant, right? So right here, then when any optical ray, light ray travels through a medium, right, its refractive index we denote it by n, and the product of velocity v becomes constant. So simply when it travels through a medium, nv equals k. Nv equals k, right? Take this down and highlight. And we have done some things already with these shapes of equations, right? When PV is a constant, P1 V1 equals P2 V2. When AV is a constant, A1 V1 equals A2 V2. Right? Now, if the product is constant, if I apply this for two instances also, that constant remains constant, right? Since that it remains as a constant, if I apply this for two media, right, then hence if the equation is applied, if the equation is applied for two different media, right? Now, since that remains a constant for two different media, what happens is, now say N1 and V1 are the refractive index and the velocity of the first medium, and that of the second medium is N2, V2. This also remains constant. This also remains constant. So as an equation, right, as an equation, then we can say N1 V1 equals N2 V2, right? That is derived from NV equals K, right? And not only for two media, right? For any different number of media, this is applicable. N1 V1 equals N2 V2 equals N3 V3 equals N4 V4 equals so on and so forth. For any different number of media, this equation is applicable, right? In this equation, 1 refers to first medium and 2 refers to second medium. We'll introduce terms after this, right? Then take it down also. N1, N2, V1, V2 will introduce, right? Will introduce. Right? Introduce terms N1, refractive index of first medium, N1, refractive index of first medium, N1, refractive index of first medium, refractive index of first medium, N2, refractive index of second medium, refractive index of second medium, right? V1, velocity at first medium, V1, velocity at first medium, V1, velocity at first medium. Then V2, velocity at second medium, V2, velocity at second medium, V2, velocity at second medium, V2, velocity at second medium. Right. Now, using the equation, we are going to define refractive index. Right now, even though I use the word refractive index, right, you don't know what refractive index is. You don't know yet what refractive index is, right? Now, we'll be seeing the definition or the definitions, because there are two definitions of refractive index in the next part. Okay, then as the next heading, write down definitions of refractive index. Next heading, definitions of refractive index. Definitions of refractive index. Definitions of refractive index. Definitions. Okay, listen. So we have two types of refractive indices, right? Under that, as Rome number 1, write down definition of absolute refractive index. Definition of absolute refractive index. Absolute refractive index. Right. Listen. Absolute refractive index means, absolute refractive index means when refractive index is defined with respect to air or vacuum medium, right? When refractive index is defined with respect to air or vacuum medium, that is called absolute refractive index, right? if refractive index is defined with respect to any other different medium other than air or vacuum, that is called relative refractive index, right? That's how we have two different types or two different definitions for refractive index: absolute refractive index and relative refractive index. Absolute refractive index is when we define refractive index with respect to air medium, air or vacuum, right? And relative refractive index is when we defined it with respect to any other different medium, right? Write down below, write down below, write down below. When refractive index of a medium is defined, when refractive index of a medium, when refractive index of a medium, when refractive index of a medium is defined, when refractive index of a medium is defined with respect to, is defined with respect to air or vacuum medium, 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 it is called absolute refractive index. 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 Right. Listen now. Now, this is what we do. To define refractive index, right? Now, as a baseline, right? One more thing to add. As a baseline, we consider refractive index of air as 1, right? That's a definition. That's a baseline. Right? As a baseline to define the other media, right? We consider refractive index of air as 1, right? We consider that as 1. Then again write down with a red pen. Refractive index of, with red pen. Next point. Refractive index of air or vacuum medium. Refractive index of air or vacuum medium. Refractive index of air or vacuum medium. Refractive index of air or vacuum medium is defined as 1. 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 Okay. So right here now. Right here. Now, we know N1 V1 equals N2 V2. Now I'm going to consider a light ray, right? I'm going to consider a light ray that is traveling from a medium to air medium, right? A light ray traveling from a medium to air medium, right? Then we know by definition n of air medium is 1. N of air medium is 1, right? Then if we apply this into the equation, then n of this medium into V of this medium equals n of air medium to V of air medium. N of air medium to V of air medium, right? Then n of this medium, V of this medium, Na is 1, then 1 times VAR. If I need to define n of the medium, right, that is given by VA over VM, no? Then VA means VAR, VM means V of this medium. Then absolute refractive index is coming from here. Then absolute refractive index is coming from here. So absolute refractive index is defined as, this is a ratio, velocity of the wave in a medium to velocity of the wave in a different medium. Then this is defined as, right, defined as the ratio between velocity of a light ray at a medium to velocity of a light ray at a different medium is defined as absolute refractive index, right? So therefore, refractive index is a ratio. It is unitless and dimensionless. That is a ratio, right? Okay, first before coming to the definition, apply the equation and write up to this point. Apply the equation and write up to this point. Apply the equation and write up to this point. Right. Right after this point. Refractive index of a medium is the ratio between velocity of the air medium to that of the medium. Right, finished. Okay, write down the definition below with red. Write down the definition below with red. Write down in red. These are definition. Write down. When a light ray travels from when a light ray travels from a certain medium to air medium, when a light ray travels from a certain medium to air medium, a certain medium to air medium, when light ray travels from a certain medium to air medium, then you have to say this: the ratio between velocity of light, the ratio between velocity of light at air medium, the ratio between velocity of light at air medium, and velocity of light at other medium, and velocity of light at other medium, is defined as absolute refractive index, is defined as absolute refractive index, is defined as absolute refractive index. is defined as absolute refractive index. Right. That's the definition. Write down below again separately. Write down below again. Refractive index is unitless and dimensionless. 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 Right. Now for this, mention few examples also. For this, mention few examples also. Right. As examples, absolute refractive index. Absolute refractive index of glass is found to be 3/2. Right. And as another popular example, absolute refractive index of water is found to be 4/3. Right. Absolute refractive index values. Right. So simply there is a ratio between velocities. Then when the velocity changes, refractive index changes. When the velocity changes, refractive index changes. Right. Mention these two also. Right. Okay, then as Rom number 2, write down Rom number 2 definition of relative refractive index. Rom number 2 definition of relative refractive index. Rom number 2 definition of relative refractive index. Definition of relative refractive index. Right. For the relative refractive index, we are going to define this based on another different medium. Right. Now, in the previous scenario, it was based on air or vacuum medium. No? Right. Air and vacuum are considered as same. And here we are going to define this based on another medium. Write down below. When refractive index is defined, 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 when refractive index is defined based on a different medium, based on a different medium, when refractive index is defined based on a different medium other than air or vacuum, based on a different medium other than air or vacuum, based on a different medium other than air or vacuum. It is called relative refractive index. 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 Relative refractive index. Right. Listen now. Now, this is when a light ray travels from one medium to the other. No? Then say medium 1 to medium 2. Medium 1 to medium 2. Right. Now, If we apply the equation again, N1 V1 equals N2 V2, right? Parameters of medium 1 is considered as 1 N1 V1 and parameters of medium 2 are considered as 2 N2 V2, right? Now, if we define the refractive index based on another medium like this, right? Based on another medium, right? V2 or V1. This is called relative refractive index. This is called relative refractive index. Right now, here, this refractive index is defined as see, when a light ray travels from one medium to the other, right? The ratio of the light ray, the ratio between the velocity of light ray at second medium to velocity at the first medium is defined as refractive index of first medium relative to second medium, right? So likewise, if that is defined with respect to a different medium, that is called relative refractive index. If that is defined with respect to another medium, different medium, that is called relative refractive index, right? Same idea. Absolute refractive index is when that is defined with respect to a vacuum, and relative refractive index is when that is defined based on another different medium, right? Now, first start from here and run up to here. Right. Okay, right. Then write down the definition below. Write down the definition below in red. Write down the definition below in red. Write down the definition below in red. Write down when light ray travels in red. This is the definition. When light ray travels, when a 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 light ray travels from one medium to another, from one medium to another, from one medium to another, the ratio between the ratio between the ratio between velocity of light, the ratio between velocity of light, the ratio between velocity of light, the ratio between velocity of light at second medium, velocity of light at second medium, velocity of light at second medium, and velocity of light and velocity of light at first medium, and velocity of light at first medium, and velocity of light at first medium is defined as is defined as is defined as is defined as refractive index of first medium, is defined as refractive index of first medium, is defined as refractive index of first medium, is defined as refractive index of first medium relative to relative to relative to second medium, relative to second medium, relative to second medium, relative to second medium, right? See, now as an example for this, say you need to find refractive index of water relative to glass. Water relative to glass, right? Then water relative to glass, right? Always 2 is coming as the denominator term, right? This is refractive index of first medium relative to second medium, no? Right? This is also called refractive index of first medium with respect to second medium, right? This is either called refractive index of first medium relative to second medium, or it is also called refractive index of first medium with respect to second medium, right? Now this is refractive index of water relative to glass, no? Then for such cases, if you need to build up the equation, right, then we know n1 v1 equals n2 v2, right? And let's consider this side as water. Then nw vw equals, right, nw vw equals ng vg, right? Now as this refractive index, what you need to find is water to glass, no? Then nw to ng, this is what we need, right? nw to ng, that is given by vg to vw, right? What we need is this. Now if these two are known, without knowing velocities even, you can find this out, no? Now what I need is this nw to ng, refractive index of water relative to glass. Refractive index of water relative to glass. Then refractive index of water means absolute refractive index of water, that is 4/3, and that of glass 3/2, right? Simplify, that is 8/9. So 8/9 is the refractive index of water relative to glass, right? So likewise, if this is defined with respect to a different medium, that is always called the relative refractive index, right? If that is defined with respect to a medium, that is called absolute refractive index, right? Take it down. And this term with 2 is always coming as denominator. That is always coming as denominator. The term with 2, that is always coming as denominator. 2 term again, the term with 2 is always coming as denominator, right? Term with 2. Write down. Right? Simple as that. Right? So far what we have discussed is, right, we discussed what refractive index is, and first you got to know that product NV of any wave or for light ray or for optical ray when it travels through a medium is a constant. Since NV is a constant, we got the equation as n1 v1 equals n2 v2, right? And then using the same equation, n1 v1 equals n2 v2, right, we define two refractive indices, right? First one absolute refractive index, the second one relative refractive index, right? Absolute and relative. Absolute refractive index is defined with respect to air or vacuum medium, whereas relative refractive index is defined with respect to a different medium, right? Simple as that. And since refractive index always gives a ratio between velocities, that's a ratio, that's a number, right? Since there is a number, that is unitless and dimensionless. That is both unitless and dimensionless, right? So that is what we have discussed so far, right? Any questions up to this point? Any questions up to this point? Anything up to this point? Does the equation is only valid for air? No, right? We have applied for any medium, no? So we assume air and vacuum are same. Yes, they are same. Not an assumption, they are same. And we must submit before tomorrow. There's a paper for this week. Is this the first week of August? You have the first paper on the first week. You have the first paper in the first week of August. Anything else? Right, quickly go through what we have done from the beginning and ask if there's anything else. Right, we'll see some examples also after this point. Right, let's see an example. Right, as an example, write down example 1. Write down. Write down. As an example 1, write down refractive index of refractive index of refractive index of medium A, refractive index of medium A, refractive index of medium A, refractive index of medium A is 7/4, is 7/4, and and refractive index of medium B, 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 medium B is 5/4, and refractive index of medium B is 5/4. A light ray enters, write down, a light ray enters, a light ray enters, a light ray enters, a light ray enters medium B, a light ray enters medium B from medium A, enters medium B from medium A. Velocity of light at medium A is, velocity of light at medium A is velocity of light at medium is velocity of light at medium is velocity of light at medium is 8 times 10 to the power 5 ms minus 1. 8 times 10 to the power 5 ms minus 1. Right? Part 1, as part 1, write down part 1. Part 1. Refractive index of medium B with respect to A. Part 1. Part 1. Refractive index of medium B with respect to A. Part 1. Refractive index of medium B with respect to A. Refractive index of medium B with respect to A. Right? Part 2. Part 2. Part 2. Velocity of Part 2. Velocity of light at medium B. Velocity of light at medium B. Part 2. Velocity of light at medium B. Velocity of light at medium B. Velocity of light at medium B. Okay, give it a try. Give it a try. Right. So I joined the class a bit late. Did you inform anything about the paper class? About the paper class, what I informed was we are going to start the graded and ranked papers next week. Right. And that's it. And if you need to check that again, when the class ends, you can go to the YouTube video and check it there. Like first 5 minutes. First 5 minutes. right? Okay, let's see. First one. I asked about refractive index of V with respect to A, no? Right. So as the first one, I asked about refractive index of V with respect to A. NB to NA. Right. This is NA. This is NB. Then NB is 5/4, and then A is 7/4. Right. 4 cancels off, and that is 5/7. And that is 5/7. 4 cancels off, and that is 5/7. And then I asked the velocity at B. Now I gave you that the ray travels from A to B, right? I gave you that this ray travels from A to B. Then this is a ray travels from A to B. Then we know N1 V1 equals N2 V2. Then from A to B, that is like NA VA equals NB VB, right? Refractive index of A 7/4, and velocity at A is given 8 times 10 to the power 5. Then refractive index of B 5/4. 5/4. Velocity of B, say that is VB, right? Then 4 to 4 cancels off. 4 to 4 cancels off. Then VB is given by subject VB. Subject VB. VB is given by 8 times 7, right? 56 over 5, 10 to the power 5, right? Then velocity of B, velocity at B, right? 50 over 5 is 10, 6 over 5 is 1.2, then 11 or 11.2, right? That is 11.2 10 to the power 5, right? 11.2 10 to the power 5 ms minus 1. Right, check with your answers, workings, if any changes. Check with your workings if any changes, right? Check with your workings if any changes, right? And even these type of MCQs are coming, right? And even they have been in the past papers also, right? So starting from this level, MCQs are coming. Starting from this level, MCQs are coming. When you grab these things from the beginning, right, this won't be a problem, right? Otherwise, now when students miss the fundamentals, foundation of optics, right, then optics is going to be kind of a headache when we are moving forward, right? So let's have a firm foundation. So today I'm laying the foundation for the thing. I'm laying the foundation. Then in optics, there are many parts coming up, like refraction, then refraction through lenses, refraction through lenses and prisms, refraction through prisms, and then real depth and apparent depth, right? Then eye defects, then optical instruments. So likewise, different parts are there. And this is still the foundation, the general things. Okay, finished? Then let's try another one. Right. Let's try another one. Example 2. Example 2. Example 2. Write down. A light ray travels from glass to odor. Example 2. A light ray travels from glass to odor. 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 And wavelength of light in glass and wavelength of light in glass and wavelength of light in glass wavelength of light in glass is wavelength of light in glass is 2 micrometers and wavelength of light in glass is 2 micrometers if refractive indices of glass and water are 3/2 and 4/3 respectively 3/2 and 4/3 respectively 3/2 and 4/3 respectively find find first one wavelength in water. First one wavelength in water. First one wavelength in water. And second one if velocity at water is 2 times 10 to the power 8 ms minus 1, if velocity at water is 2 times 10 to the power 8 ms minus 1, frequency of light ray. Right? So in the first question I need lambda in water medium. Right? In the second question I need frequency of this light ray. Okay, start it. Start now. There can be small links with the waves parts, right? So when we need something from the learnings of waves, feel free to use anything from what we have learned in waves. Right, any answers? One 1.77 micrometers. Let's see. We'll start in 2 minutes. Quickly find the answers. Right? We need wavelength in order and frequency of this optical ray. Right, any other answers? And the good news is now 26 batch classes are over and you are graduated to the senior batch, right? So you are the senior batch now. That's a good news. And the bad news is, you are having the exams just in 52 more weeks. Just in 52 more weeks, right? You will be also having the exam just in 52 more weeks. And 26 batch is having the exam in 9 days, right? And you are having in 52 weeks, right? So time flies and time goes, and continue your good work to the same momentum, in the same rhythm up until next August, right? Now all dates are like finalized, no? So therefore they are not going to change again. You have just 52 weeks for the exam, right? And 28 batch is also going on. And the other thing is, now this time O levels will be in December this year. Then 29 batch is also starting in December, right? 29 batch is also starting in this year December, right? So you are getting older and older, right? You are getting older and older, right? Okay, let's see first one. Now this is a light ray travels from glass to water. That is a light ray travels from glass to water. Glass to water, right? So we know N1 V1 equals N2 V2, right? N1 V1 equals N2 V2. Then if you need to convert this into lambda, if lambda is given, right? If I need to convert this into lambda, we can use something from waves. We know V equals F lambda, right? This is coming from waves. V equals F lambda. V equals F lambda. And under waves, under refraction of waves, we have discussed that frequency remains unchanged, right? At any wave phenomena, frequency remains unchanged. Now these are refraction, no? So still frequency remains unchanged. Then I can write this as in glass, and for V F lambda, then say frequency is F and lambda is lambda glass. In water, frequency is still the same and lambda is lambda water. Now frequency cancelled off. Then final equation is this: N glass to lambda glass equals NW to lambda W. Then N glass is given 302. Lambda glass is given 2 micrometers. Right? NW is given 4, 3. Then lambda W is what we need. Now to do 2 cancels. Then lambda W equals 904. Lambda W equals 904. Right? 904 is 2.25 micrometers. 2.25 micrometers. Right? Then wavelength is 2.25 micrometers. Right? And then we need frequency. To find frequency, right? Can apply V equals F lambda. Right, now I'm going to apply this for water because velocity of water is given for water. Then velocity at water is 2 times 10 to the power 8. We need frequency and lambda at water is 2.25. Right, for the ease of simplifying, I'm writing it as 904. 904, that is in micrometers, right? Then 10 to the power minus 6. Now frequency is given by 8 over 9, 10 to the power, right? 8 6 means 14. 8 over 9, 10 to the power 14, right? What's the value? 8 over 9. 8.8. Right, then that is 8.8 times 8.8 times 10 to the power 13. 8.8 times 10 to the power 13 hertz. Frequency is in hertz. Right? So likewise, there can be some small links with the wave things also. Right? Write down if any changes. Okay, right? Check your workings and check if any corrections. Right? So final answers. Lambda at water is 2.25 micrometers and frequency of the wave is 8.8 times 10 to the power 13 hertz. 8.8 times 10 to the power 13 hertz. Right, final answers. Okay, write down below with the red pen. Write down below with the red pen. Write down below with the red pen. Frequency remains unchanged. In red, frequency remains unchanged. Frequency remains unchanged. Frequency remains unchanged. Frequency remains unchanged. When a wave travels from, frequency remains unchanged when a wave travels from. Frequency remains unchanged when a wave travels from one medium to another. When a wave travels from one medium to another. When a wave travels from one medium to another. When a wave travels from one medium to another. When a wave travels from one medium to another. Right? Within brackets, diffraction. Within brackets, diffraction. Within brackets, diffraction. Within brackets, refraction. Right. Now, look at the board again. Right. So we know for any wave, for any light ray, N1 V1 equals N2 V2. Right. And if we use V equals F lambda to expand this, right, I can write this as N1 is instead of V1 F lambda, then F lambda 1 and N2 F lambda 2. Right. We know frequency is unchanged. Right. Frequency unchanged. then frequency cancels off and n1 lambda 1 equals n2 lambda 2 comes. So directly, if we need the relationship between lambda and refractive index, here we go, right? If we need a relationship, a direct relationship, if we need a direct relationship between refractive index with wavelength, right? We can directly apply n1 lambda 1 equals n2 lambda 2. That is derived from n1 v1. That is derived from n1 v1, right? And hereafter we can directly use this as a direct equation, right? Start from here and take it down. Start from here and take it down. Since we have already introduced n1 and n2, introduce lambda 1 and lambda 2 here. Introduce lambda 1 and lambda 2 here. n1 and n2 are already introduced, right? n1 and n2 are already introduced, right? So introduce lambda 1 and lambda 2 here. Introduce lambda 1 and lambda 2 here. Okay, lambda 1, wavelength of first medium. Wavelength of first medium. Lambda 2, wavelength of second medium. Wavelength of first medium and wavelength of second medium. Wavelength of first medium and wavelength of second medium. Wavelength of first medium and wavelength of second medium, right? Okay, now we are going to move on to the next part. Right? As the next heading, write down refraction of light. Next heading, refraction of light. Refraction. Refraction of light. Refraction of light. Listen now. Listen. Now about refraction. Right, under waves, we discuss about refraction. Now we are going to convert the same idea to light, to optics in this part. Right, under waves, we discuss about 5 wave phenomena. Right, reflection, refraction, diffraction, interference, and polarization. Right, and from that, now we are in refraction of light. Right, and as I explained at the very beginning, since optics is also coming from electromagnetic waves, right, all the features of electromagnetic waves are valid here for optical rays, right? All the features of electromagnetic waves are valid here for optical rays because it is coming from electromagnetic waves, that is coming from electromagnetic spectrum, right? Okay, then I explain what refraction is in waves. What is refraction? What is refraction? We explain the same thing in waves. Refraction. Refraction is the bending of light rays, right? That's a bending of light rays due to change of media, right? Bending of light rays, that is also called deviation of light rays due to change of media, right? Bending or deviation of light rays due to change of media is called refraction of light. Bending of a wave or deviation of a wave due to change of media is called refraction of waves, right? Now here I'm going to specify this into light because now we are in optics, right? Write down below bending, write down below bending slash deviation, bending slash deviation bending slash deviation of light, deviation of light due to change in media, due to change in media, due to change in media, due to change in media is called refraction. 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 Okay, listen now. When it comes to refraction, there are two laws of refraction, right? Now we have recalled that in waves also. Now again we are going to recall here because we are going to rely 100% on these refraction laws hereafter, right? When we are moving on refraction, general refraction, refraction through prisms, refraction through lenses, and so on, right? So as the next heading, write down laws of refraction. Next heading, laws of refraction. Laws of refraction. Laws of refraction. Right, listen. Now when it comes to refraction, right? When it comes to refraction, there's a jargon that you should know first, right? Refraction and optics, actually. There's a jargon that you should know first, right? Let's say a light ray travels from a dense medium to a rare medium, right? Dense and rare means, listen now, listen carefully. Dense and rare means, right? Dense and rare means, right? There is something defined based on the refractive index, right? Simply, when we compare two media, the higher refractive index, the medium with higher refractive index is called the dense medium, and the medium with lesser or the lower refractive index is called the rare medium, right? Then we can't define a medium as dense or rare because it changes with the other medium that is with contact, that is in contact, right? As an example, if I compare say air and water. If I compare air and water, refractive index of air is 1, refractive index of water is 4/3. Then in that case, water is dense. And again, if I compare, right? Again, if I compare glass with water, refractive index of glass is 3/2, 1.5, right? And refractive index of water is 4/3, 1.33. Now in that case, water is rare, right? So likewise, dense and rare is always relative. That is always relative. That changes with respect to the other medium that is in contact, that is in the system, right? So simply keep this in mind as dense means the higher refractive index, right? And rare means the lower refractive index. Now if a light ray travels from dense to rare, right? Say this light ray travels from a dense medium to a rare medium, right? This normal line which is drawn at the incident point, right? This normal line drawn at the incident point, right? Normal drawn at the incident point, right, is called normal. That is called the normal. Right? And when light ray travels from dense to rare, the bending is always away from the normal. Dense to rare. Now its original direction is this, no? Now if you need to compare this original direction with its bending direction, now original direction is this if it is not refracted. Now as a result of refraction, when light ray travels from dense to rare, it bends away from normal. Now from this original direction, it bends away from the normal. And this is where it is going to go. Something like this. This is where it is going to go, right? And the next thing is when measuring angles. Next thing is when measuring angles. Right. Before angles, there are names for these rays. This is called incident ray. This is called incident ray. Incident ray. And this is called refracted ray. Refracted ray. Refracted ray. Right. And this is the normal. And always angles in optics are measured only with the normal. Angles in optics are measured only with the normal. Right. Angle between incident ray and the normal is called angle of incidence I. Right. An angle between the refracted ray and the normal. Refracted ray and the normal is called angle of refraction R. Right. So I is angle of incidence. This is a jargon we should know. Angle of incidence and R angle of refraction. Angle of incidence and angle of refraction. Right. And the angle between the original direction of light ray and the final direction of light ray. Right. Original direction of the light ray and the final direction of light ray. Original direction was this. Original direction was this. And the final direction is this. Angle between original direction and the final direction of the light ray is called D. That is called angle of deviation. Right. And D angle of deviation. Right. Angle of deviation. And this line which separates the two media, this line which separates the two media is called the interface or the common surface. Right. This line which separates the two media is called interface, just as hydrostatic interface. Right. Or that is called the common surface. That is also called the common surface. Right. Now, before seeing laws of refraction, right, first we have to have an idea about this. Right. And I know that you have done this in O levels also. Right. Now again, have to recall you have done this in O levels like 1.5 years back. Right. Recall again here. Right. Angle of incidence, angle of refraction, incident ray, refracted ray, and the angle between the original direction and the final direction of the light ray is angle of deviation. Right. Take it down. Take it down. Take it down. Use different colors if you need more clarity. Use different colors if you need more clarity. Right, and make it clear. Make it clear to you. Okay, check again. Check again. Incident ray, refracted ray, interface or common surface, dense and rare media, normal, normal, right? And I, angle of incidence, R, angle of refraction, D, angle of deviation. Right, now we are going to write the two laws first. We are going to see the two laws first, right? Refraction laws. There are only two laws about refraction, right? So mention the laws as 1 and 2. Mention the laws as 1 and 2. First one. Write down. Write down. Write down. All incident ray, all incident ray, all incident ray, comma, refracted ray, all incident ray, comma, refracted ray, incident ray, comma, refracted ray, and normal drone, and normal drone, and normal drone, and normal drone at the point of incidence, normal drone at the point of incidence, normal drone at the point of incidence. Lie on the same plane. 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 Second one. Second one. Second law. Second law. Write down. Ratio between. Second law. Ratio between. Ratio between. Ratio between. Sine value of. 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 Sine value of. Angle of incidence. Sine value of angle of incidence. And sine value of angle of refraction, and sine value of angle of refraction, and sine value of angle of refraction, and sine value of angle of refraction. Is constant. Is constant. is constant. Right? Say it again. The ratio between sine value of angle of incidence and sine value of angle of refraction is constant. Is constant. Within brackets, write down Snell's law. Within brackets, write down Snell's law. Within brackets, Snell's law. Right? And below that law again, sine I over sine R equals K. Constant. Right? Mention this also. Right? Mention this also. When you are asked to write refraction laws, you can't write the second law as Snell's law. You have to write the Snell's law in words, right? Not the name of the law. No, you have to write the law in words. If you are asked to write refraction laws, right? That is called Snell's law. Okay, listen now. Listen. Now, by Snell's law, there's another result that we are going to prove. Listen. By Snell's law, we know sin I over sin R is a constant, no? Is a constant. And after several researchers, Snell found that the ratio between sin I to sin R, the ratio between sin I to sin R is also same between refractive indices, right? So experimentally he found that the ratio between sin I to sin R is same as the ratio between refractive indices, and then K was replaced by N2 over N1. And now when this is cross multiplied, we can get another equation as N1 sin I equals N2 sin R. N1 sin I equals N2 sin R, and this equation was found, and this is stated as Snell's equation, right? So this is what we call the Snell's equation. Snell's equation, right? The main equation we have in refraction, Snell's equation. The main equation, right? Main equation we have in refraction, Snell's equation, right? Then start from here and right up to here, we have to introduce terms also, right? The terms are N1, N2, IN, R. N1, N2, IN, R. Right? Take it down and come up to this point. Right? Right, introduce terms. N1 refractive index of first medium. N1 refractive index of first medium. N1. N2 refractive index of second medium. N2 refractive index of second medium. Right. Then I angle of incidence. I angle of incidence. Angle of incidence or angle of refraction. Angle of incidence and R angle of refraction. Right. Right. Then as a note, write this down separately as a note. As a note, write down. As a note, write down. As a note, write down. Write down. When a wave travels from, as a note, write down. When a wave travels from, a dense medium to rare medium. When a wave travels from a dense medium to rare medium. A dense medium to rare medium. When a wave travels from a dense medium to rare medium. Dense medium to rare medium. It bends away from normal. It bends away from normal. It bends away from normal. Right. Second point. When a wave travels from a rare medium to dense medium. A rare medium to dense medium. It bends towards normal. 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 Right. Okay, that's it for the note. Now we are moving on. As the next heading, write down refraction and partial reflection. Refraction and partial reflection. Next heading, refraction and partial reflection. Next heading, refraction and partial reflection. That is also called lateral reflection. Right? Refraction and partial reflection. And partial reflection. Partial reflection. That is also called lateral reflection. That is also called lateral reflection. Right? Refraction and partial reflection. Listen now. Look at the board. Right. Say these two are two different media. And this one is a rare medium. And say this is a dense medium. Right. A light ray travels from the rare medium to dense medium. From the rare medium to dense medium. And this is the normal drawn at the point of incidence. Now when it travels from rare to dense, it bends towards normal. No? It bends towards normal. Now original direction of this ray is this. Original direction is going to be this. Then from that direction it bends towards normal like this. From that original direction it bends towards normal like this. Right. Now this is our incident ray as usual. This is our incident ray as usual, and this is our refracted ray as usual. Refracted ray as usual, right? And we know all angles are measured only with the normal. Angle between normal and the incident ray is angle of incidence, I. Angle between normal and the refracted ray is angle of refraction, R. Right? That we knew. That we knew. Right. Now, the new thing. Listen. Now the new thing. When a refraction takes place, right? When a refraction takes place, right? The light ray is never going to 100% refracted. When a refraction occurs, the light ray is never going to refracted 100%. Right? What happens is only 80% is refracted. Now, if this light ray is say intensity as an intensity, this light ray is 100%. Around 80% of light ray is refracted. Around 80% is refracted. And when this light ray collides or hits on the interface between two media, the remaining 20% is reflected back to the same medium. Remaining 20% is reflected back to the same medium, right? Remaining 20% is reflected back to the same medium. Then what happens here is, right, this reflected back to the same medium like this. Reflected back to the same medium. From laws of reflection, we know angle of incidence and angle of reflection are same. Then if this is I, this is also I, it is reflected back. And this ray is called partially reflected ray. And this phenomenon is called partial reflection. This is called partially reflected ray. Partially reflected ray. This phenomenon is called partial reflection, and the remaining 20% is here. So this is what happens. This is what happens when a refraction occurs. This is what happens when a refraction occurs. Right? The light ray is never going to refract 100%. Right? That is never going to refract 100%. Right? What happens is only 20% is only 80% is refracted, and the remaining 20% is reflected back. That is called the partial reflection. Right? One example, listen. One example for this is, right, now think of a scenario where you are looking through a glass. You are looking through a glass. Where you are observing something through a glass. Right? You are observing something through a glass. Right? When you observe something through a glass, right, you can see what is at the other side of the glass. No? Right? If you can see what is at the other side of the glass, that is because of refraction. But if you were careful and if you carefully look at it, right, you can see our own image. You can see our own image is also on the glass. Right? We can see our own image is also on the glass. That is because of partial reflection. And another scenario is say you are observing fish in a pond. You are observing fish in a pond in ground. Right? Observing fish in a pond. Right? When we observe fish in a pond, we can see fish, no? Right? We can see fish. You are seeing fish because of refraction, because you are at air medium and fish is inside the water medium. So if you observe fish, that is because of the refraction. And if you carefully look at it, at the same time, you can see your own image reflected from the water surface. Right? You can see your own image reflected from the water surface. That is because of partial reflection. And if you notice carefully, right, our own image is always kind of faded. That is less intense. Right? That is less intense. Intensity is less in our own image than the fish. The reason is this: our own image is due to 20% and the fish is due to 80%. Right? So we will see fish with a higher intensity, and you will see our own image with a lower intensity of 20%. Right? This phenomenon is called partial reflection. This phenomenon is called partial reflection. Right? Take down the diagram. Take down the diagram. right? Tie down. I have clear diagrams, otherwise when you refer again, if you can't see what you have done, there's no point of that, no? Okay, finish. Right down below. Right down below. Right down below. Everywhere a refraction occurs. Right down below. First point. Right down below. First point. Everywhere a refraction occurs. Everywhere a refraction occurs. Everywhere a refraction occurs. Everywhere a refraction occurs. There's a partial reflection of. 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 There's a partial reflection of about 20%. There's a partial reflection of about 20% occurs. There's a partial reflection of about 20% occurs. There's a partial reflection of about 20% occurs. Right? Partial reflection of about 20% occurs. Next point. Next point. Only 80% of the ray. Only 80% of the ray. Only 80% of the ray. Only 80% of the ray is refracted to the other medium. Only 80% of the ray is refracted to the other medium. Only 80% of the ray is refracted. Only 80% of the ray is refracted to the other medium. Only 80% of the ray is refracted to the other medium. Only 80% of the ray is refracted to the other medium. Right. Okay, now let's see an example. Right, I'm going to give you a small exercise as an example. Listen. Listen. Okay, listen. Okay, say this is a mirror. Right, and these ones are different media. These ones are different media. Different media. Right? Different media. say n1, n2 and n3. Their refractive indices are n1, n2 and n3, right? And n1 is greater than n2 greater than n3, right? And this is air. This is air. This is an example. No? This is an example. This is air. Now a light ray enters this from the air medium. Right? Listen. A light ray enters from the air medium. A light ray enters from the air medium. Right? Like this. Right? And here it enters from n1 to n2. N2 is a air medium. It bends away. It bends away. Right? And it is reflected here. And at this point again, it enters from n2 to n3, a air medium. So it bends again like this. Right? Say these light rays are. Say these light rays are. Let me draw the partial reflections also before I label them. Now here we have one refraction and one partial reflection. Right? And sometimes when it comes to questions, the partial reflection ray is also given as a solid ray to you to identify whether it's a partial reflection or refraction. Otherwise, when we draw as a standard, we draw a partial reflection with dotted lines. But when it comes to questions, there have been questions, right? The partial reflection is also given just as a solid ray, and you have to do something and you have to work on it and identify whether it's a refraction or a partial reflection. Right? Now this is the first partial reflection. And here you have another one, right? And here another one, right? Now let me label these rays as, right? Let me label these rays as I1, I2, I3, I4, I3, I4, I5, I6, I7, I8. Right. So what we are going to find is, right, I need the descending order of intensities of these light rays. I need the descending order of intensities of these light rays. Okay. Write down as an example. Write down. Find the descending order of. Find the descending order of. Find the descending order of. Find the descending order of given light rays. Descending order of given light rays. Find the descending order of intensities of, sorry, yeah. Find the descending order of intensities of given light rays. Find the descending order of intensities of given light rays after being refracted. Find the intensities of, sorry, find the descending order of intensities of given light rays after being refracted. After being refracted. Okay, take down the diagram. Take down the diagram, and they are labeled as I1, I2, I3, I4 likewise. Right? Find the descending order of these light rays. And if there are equal ones, you can say them as equal. Right? If there are equal ones, you can say them as equal ones. Right? So I need that correct relationship. Right? Okay, any answers? Okay, any answers? Fine. See, now first thing is you have to identify whether a given ray is a refraction or a partial reflection. Right? Whether a given ray is a refraction or a partial reflection. Right? Now it's like this, no? Say this is a refraction. Right? This is a refraction. This is a refraction. Right? See? Now let's assume this intensity as 100% for the ease of doing this. Let's assume this intensity as 100%. Let's assume. Now if there is 100%, this becomes 20%, no? This is a partial reflection. And this becomes 80%. This becomes 80. Right? And now this is a partial reflection again. Right? This is a 20% again from 80%. Then this is 20% from 80%. Huh? This is 20% from 80%. That is 16%. Right? 20% from 80% is 16%. Then this one, no? This one is 80% of 80%, no? That is 80% of 80%. That is 64% from the original. Right? 64% from the original. And this is a reflection. This is a mirror. Due to the mirror, this is a reflection. Then I3 and I4 are same. I3 and I4 are same. Because there is a reflection, not a refraction. I3 and I4 are same. And from I4, this is again a refraction. Then this is 80% of 64%. That is 80% from the 64. Right? Because what incidence here is 64% only. Then this is 80% from the 64. Then what's the value? 80 into 64 means 51%. That is 51%. Right? So this becomes 51%. And its partial reflection is here. This is 20% of that 64. 20% of that 64 is here. 20% of the 64 is 32, right? 32 means 3.2. Sorry, 12.8. 128, then 12.8%. Right. So likewise, see, now I have the final intensities. Now I have the final intensities with respect to this 100. These are the final intensities with respect to 100. 20, 16, 64, 51, 12.8. Then arrange them in the descending order. I1 is the highest. I1 is the highest, and the second highest is here. I2 80%. I2 80%, right? And then 64, I3 and I4 are equal. Then I3 equals I4. I3 equals I4. Then 51, I5, 51, I5, right? And then 20, I6, 20, I6, and then 16, I7, right? And finally 12.8, I8, right? So this is the order. So likewise, we can arrange them. By checking whether it's a refraction, partial reflection, or a reflection, right? And when it comes to questions, you won't be given as dotted lines. I mean, partial reflection won't be given as dotted lines in most of the cases. Now, in such cases, you have to carefully check the refraction and you have to carefully identify the refraction and the reflection. Okay, take it down. So likewise, we can do a small, a simple math. Likewise, you can do a simple math and find it out. Likewise, you can do a simple math and find it out when we need. Right? And you will see these type of questions sooner in the papers. Right? So when you get this in papers, now you should be able to try those questions with this knowledge you gain. Right? Take it down. Okay, right. Write down below with the red pen. Write down below with the red pen. Write down below with the red pen. All 100% is reflected. All 100% is reflected. All 100%. All 100%. All 100% is reflected. Is reflected back to the same medium. Is reflected back to the same medium in reflection. Is reflected back to the same medium in reflection. Back to the same medium in reflection. Okay, let's move on. Right, let's move on. As the next heading, write down. Refraction, critical angle, and total internal reflection. Next heading. Refraction, critical angle, and total internal reflection. Refraction, critical angle, and total internal reflection. Right. Listen now. Right. First one here. Right. See. So this is a normal refraction. And let's assume this has a dense medium and this has a rare medium. And as a light ray travels from dense to rare. Right. A light ray travels from dense to rare. Then if it is a normal drawn at the point of incidence, right? Dense to rare means this bends away from normal like this, right? This is I angle of incidence. This is R angle of refraction, angle of incidence and angle of refraction, right? Now, in this case, we can clearly see that I is less than R, right? I is less than R because R is a high angle. This has bent away from the normal. I is less than R, right? And if I draw the partial reflection is here. Partial reflection is here, right? With same angle, right? Then we know if this is 100%, 20% is here, and 80% is here. Right? Take it down first. Take it down. Take it down. Right, listen carefully. Now, if we gradually increase, listen and look at the word. If we gradually increase the angle of incidence, right? If we gradually increase the angle of incidence, right? If we gradually increase the angle of incidence, we know R is greater than I. No, since R is greater than I, when I increases, R also increases. When I increases, R also increases, right? So what happens is, when I increases, R also increases. When I increases, R also increases. When I increases, R also increases. Since R is greater than I, right? R reaches 90, a right angle before I reaches a right angle. Now, when I increases, R increases, but R is greater than I, then R reaches 90 before I reaches 90. Then at that point, this is what happens. At that exact point, right? That we call the critical angle. And at that exact point, what happens is this. For some value of I, right? angle of incidence becomes 90. Angle of refraction becomes 90. And angle of incidence at this point is called critical angle. Angle of incidence at this point is called critical angle C. Critical angle C. Right? Now, this is a special case. This is a special case because the refracted light ray travels through the common interface, common surface. Now, in this case, I equals C, R equals 90. I equals C and R equals 90. That is called the critical angle. That is called the critical angle. Right? Now, still, if I draw the partial reflection, that is still there. Partial reflection is still there. Then if I draw the partial reflection, this 100% is here and 80% is only refracted, and this 20% is still here, right? With this C. That set is called the critical angle. Take it down. And before taking down, we didn't write this, right? Write down below. When I increases, write down. When I increases, R increases. 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 Hence, R reaches 90 degrees. Hence, R reaches 90 degrees. Hence, R reaches 90 degrees. Hence, R reaches 90 degrees before I. Hence, R reaches 90 degrees before I. R reaches 90 degrees before I. R reaches 90 degrees before I. Right. As number 2, row number 2, critical angle, take it down. As row number 2, critical angle, take it down. Take it down. Okay. Listen. Right. Now, a question again. A question again. Listen. Now, this is what happens when light travels from dense to rare. Right? So, this is what happens when light travels from dense to rare. This is what happens when light travels from dense to rare. Now, what if the vice versa occurs? What if a light travels from rare to dense? Still, can there be a critical angle? Right? But my question is, now this I have drawn when a light travels from dense to rare medium. Right? If a light travels from rare to dense, the other way, can there be a critical angle or not? Yes or no? If yes, what's the reason? If not, what's the reason? Any thoughts? What do you think? Right? If needed, you can draw and see. If needed, you can draw. You can draw it on a piece of paper and check whether what happens. Right, listen. No answers. Listen. Now, if a light ray travels from a rare medium to dense medium, if a light ray travels from a rare medium to dense medium, right, it bends towards normal. No? It bends towards normal. Now, in that case, I is greater than R. I is greater than R. And when I increases, right, when I increases, I is going to reach 90 before R. I is going to reach before I is going to reach 90 before R. Right? Then refracted ray is not going to go through the interface. Refracted ray is not going to go through the interface, then there's no critical angle in this case. There's no critical angle here. There's no critical angle here. Right? We can't make refracted angle 90 at any point. Right? So therefore, critical angle is only here. Mention this with a red pen. Somewhere here. Mention this with a red pen. Somewhere here. Mention this point in red. Write down. Critical angle occurs only. Critical angle occurs only. Critical angle occurs only. Critical angle occurs only from a dense medium to rare medium. Critical angle occurs only from a dense medium to rare medium. Critical angle occurs only from a dense medium to rare medium. Critical angle occurs only from a dense medium to rare medium. Only from a dense medium to rare medium. Right. Look at the board again. Right now, if I is further increased, if or when I is further increased, when I is further increased, when I is further increased, right? From the critical angle also now I is increased, right? Now when I is increased further from this point, when I is increased further, right? Now R tries to increase further. Now this is already at 90, that is already at 90, and it travels through the interface. It travels through the interface, right? When that tries to increase further, right, it is going to turn back to the same medium. That is going to turn back to the same medium. Right, that is going to turn back to the same medium. When it turns back to the same medium, that is not a refraction anymore, because only one medium is involved. That is a reflection. That is a reflection. Even though there are two media, it turns back to the same medium. Right? If there is inside the same medium, there is a reflection, not a refraction. Then, when this happens, right, what happens is now this is going to reflect it completely back to the same medium. It is going to reflect completely back to the same medium. When this angle is increased, beyond the critical angle. When this angle is increased beyond the critical angle, when this angle is increased beyond the critical angle, okay, say this is theta now, this is going to reflect back to the same medium, right? Then if this incidence ray is 100%, now when it is reflected back, this was already a reflection of 20%, right? This was already a reflection of 20%, and with that 20%, that 80% adds up, and the total 100% is reflected now. Total 100% is reflected now. With this 20% of partial reflection, the 80% from the reflected ray here adds up, and it makes a 100% reflection, right? That is called a total internal reflection, right? Because totally reflected, no? This is not a total reflection, this is a partial reflection. That's the difference. This is a partial reflection, only 20%, and this is 100%. That is totally reflected, so that is called a total internal reflection. Then the dense medium and a rare medium. And in this case, right, in this case, there's no refraction. Then in this case, I is greater than C. In this case, I is greater than C. Right? Then write down below. When I is further increased. When I is further increased. Right, as the topic, write down. Number 3, yeah, row number 3, total internal reflection. Right, total internal reflection is this 100%. Total means that, right, that's the difference between total and partial. Right, then total internal reflection, and take it down. Right. Okay, write down below as the next heading. Definitions of critical angle and total internal reflection. 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 But under that again, take down the heading as critical angle. And write down the definition in red. Write down. When a light ray travels, write down the definition in red. When a light ray travels from a dense medium to rare medium. When a light ray travels from a dense medium to rare medium. When a light ray travels from dense medium to rare medium. Angle of incidence when refracted ray travels through the interface. 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 When refracted ray travels through the interface between two media. interface between two media. Travels through the interface between two media is defined as travels through the interface between two media is defined as critical angle. 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 Defined as critical angle. Okay. Then next in total internal reflection. Next in total internal reflection. Total internal reflection. Right. Write down the definition in red. Write down the definition in red. Write down in red. When a light ray travels, when a light ray travels from a dense medium to rare medium, when a light ray travels from a dense medium to rare medium, when a light ray travels from a dense medium to rare medium, the phenomenon of reflecting the total light ray, the phenomenon of reflecting the total light ray, the phenomenon of reflecting the total light ray, phenomenon of reflecting the total light ray back to the same medium, back to the same incident 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 medium. When angle of incidence is greater than, 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 when angle of incidence is greater than critical angle, when angle of incidence is greater than critical angle, is called total internal reflection, is called total internal reflection, is called total internal reflection, is called total internal reflection. Right. So those are the those definitions of critical angle and total internal reflection. Right. Now separately write down below with an asterisk mark. Separately write down below with an asterisk mark. Partially reflected 20%. Partially reflected 20%. Partially reflected 20%. And refracted 80%. And refracted 80%. And refracted 80%. And refracted 80%. Is added together. Is added together. Is added together. Is added together. And reflected back and reflect back and reflects back and reflects back and reflects back and reflects back in total internal reflection and reflects back in in total internal reflection and reflects back in total internal reflection and reflects back in total internal reflection. Right? And next point, use a red pen. Next point, use a red pen. Next point, use a red pen. Both critical angle and total internal reflection. Both critical angle. Both critical angle. Both critical angle and total internal reflection. Both critical angle and total internal reflection is only from dense medium to rare medium, 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 is only from dense medium to rare medium. Okay. Listen now. So basically, right, this is the foundation here for the first part in optics, right? This is the foundation here for the first part in optics, right? And since general refraction things are over now, we are starting the sums. We are starting the sums in refraction parts next week onwards, right? And the other things coming up are, right, first we'll do some sums using this, and then real depth and apparent depth, refraction through prisms, refraction through lenses, right? So under refraction, all three are coming up. And next week, our plan is we'll be starting the sums here in refraction and going to move on beyond, right? Then that's it. And basically, we have covered the fundamental theory part here, or the foundation theory part here for optics to get the start. Since we are starting the sums and the rest next week, right? Go through these things again and again and familiar yourself with these things, right? Refraction, partial reflection, Snell's law, right? N1 equals N2 V2, and absolute refractive index, relative refractive index, or likewise the jargon and all that you have to be familiar, right? Okay, then we'll wrap up for today, and next week we are continuing from this point onwards, right? Then we'll wrap up. Stay safe and do safe and work hard, right? See you in the next class. Good night and goodbye. See you.